This is our final sequence. So in this sequence, we will violate just about everything that we have learned in this course. Okay, just to show you that rules and abstractions only take you this far. At the end of the day, we made a set of assumptions, but as long as you work within those assumptions, you are okay. However, in practical life, many of these assumptions are violated, and things do not quite behave as we expect them to. Okay, so you have to be very careful here and understand where the abstractions are violated. And in many cases, you really have to go back to fundamentals and do things again. So recall that we started out our life building a nice little EECS playground. And we got into that playground by making the assumptions of the lumped matter discipline. And there were three key assumptions. One assumption was that we were not going to have any charge buildup inside our elements, any net charge buildup inside our elements. Okay, notice that even for capacitors, the net charge buildup on both the positive and negative plates is zero, so they satisfy our discipline. The second was d phi by dt was going to be zero outside our elements. And there was a third assumption. Okay, we didn't dwell too much on it, but we did mention it, and it's also in the textbook. The third assumption of the lumped matter discipline was that our signal speeds of interest would be substantially lower, okay, than the speed of light. Okay, that's the third key assumption, that is the signal speeds of interest are such that they are much slower than the speed of light. Okay, so keep these three assumptions in mind. Okay, 1, 2, and 3. And as we go through the various things that we do today, we will try to understand what is going on, and we will see some really strange stuff happening here. So we're going to start with what I call the double take. So consider the following little scenario. Okay, so suppose I have a voltage source Vi, and that voltage source connects through some resistor R. Okay, and I can measure and observe the voltage of V0 at this point. Now let's further assume that from this point I have a bunch of other wires going to different parts of the circuit. I may have a wire going here. I may have another wire going here. I may have a third wire going here. And that wire may connect to some other pieces of circuitry, an inverter in this case. And then from the inverter, I may have a connection going to something else. All right. Now let me assume that my input voltage takes a 0 to 1 transition. Okay, so it goes from 0 to 1 and takes a step transition. Okay, so this could be a 0 here, and then I make a transition to a logical 1 in that manner. So let's look at some fun stuff. So let me draw the waveform that I expect at V0 on the right hand side. So if I get a step at the input, okay, if I get a 0 to 1 step at the input, okay, I expect, so let's say my input goes up like this. So this is my time axis, and this is a Vi. So let us say that at some point in time, okay, I take a step transition from 0 to 1. Okay, let's say the time at which I take the step transition from 0 to 1 is t is equal to 0. So let us say at time t equal to 0, my input makes a step transition like so. Okay, so for fun, let us say that goes from 0 to 5 volts. Now, what I expect from all that I've learned so far, what do you expect at V0? Okay, what I expect at V0, given that I'm not connecting my circuit anywhere, in that I have an open circuit here, so this input connects to an open circuit here. I'm telling you it's an open circuit. And let us say that this part 2 goes to, let's say for example, it might go to some other gate. Okay, and there is an infinite resistance at the input of the gate, and so is the input resistance here, that is infinity as well. So given such a scenario, my input step that goes from 0 to 1 or 0 to 5 volts, I should see the same thing reflected at V0. So at V0, I should see the exact same kind of behavior. I expect to see at time t equal to 0, I expect to see a nice little rise from 0 to 5 volts. So right here, I expect to go up to 5 volts and settle down really nicely. Okay, let me clean that up a little bit. Okay, So 0 to, let me call that 5 volts. I jump up to 5 volts. That's what I expect. Okay, so I expect this. Okay, if everything that I've discussed so far, that you've learned so far is true, then at V0, I expect a transition from 0 to 5 volts, much like there was a 0 to 5 volt transition at the input. But I'm going to show you a demonstration where you are going to see something totally strange. Okay? What you will observe here will look like this. It is something that we are completely unprepared for. What we're going to see is that at time t equal to 0, I start to see V0 go up. Just like I expect, I do start to see V0 go up. But the funny part is, once it reaches 2.5 volts, something really funny happens. It goes like this and continues on for a while, and then it bumps up and goes up to 5 volts. It's as if it began to go up to 5 volts, and somewhere along the way here it says, you know what, I'm going to take a siesta. I'm going to take a break. And so here it goes on at 2.5 volts in the forbidden region pretty much, and stays there for a while, and then suddenly it's, oh yeah, you know what, that was supposed to go up to 5 volts. Oh yeah, let's do that. Boom, and it goes up to 5 volts. Okay, so let's call this time t, and let's say this is some time 2t. We'll see the significance of t and 2t later, but some interval of time, 2t later, it decides to go back up to where it should have been. Okay, so it starts off by going to 2.5 volts, doesn't go all the way up to 5. It meanders at 2.5 volts for a bit, and then whoop, suddenly it says, oh, I got to go up, and it goes back up to 5 volts. Okay, so this is very, very strange. I did not expect this. Okay, totally did not expect this. And the problem with this is that you might ask, okay, so what's the problem with this? Well, the problem with this is that this signal is wandering around in the forbidden region. And if I take the signal in the forbidden region and I connect this signal to this little gate here, like so, this gate is going to say, huh? Okay, it is going to get confused. It's going to propagate some confused signal. And worse yet, my digital discipline said that if my input was something in the forbidden region and not valid, then all bets were off. I did not need to have any specific way in which I, as a gate, could produce an output. Okay, so really, really bad things will happen if things meander around in the forbidden region. Okay, but this is a true story, and this can happen. So before we go on and try to understand what's going on, let me go and show you a little demonstration. Okay, I'll do a quick review and show you a quick demonstration to see that in real life, this can indeed happen. Okay, in the video, you will also see a person. Okay, you'll also see a person walking back and forth. And you will understand later on in the sequence why that person is so busily walking around in the background while I am talking to the students about this demonstration. Okay, the student is walking around in the back. Okay, let's try to understand what is going on here. And first of all, we will see that my signal can behave really weirdly. And the amazing thing is that I haven't told you anything at all. You haven't learned any of the tools in this course to explain this kind of behavior. Okay, so unless you've read some other stuff based on what you've seen in this course, you should not have any tools whatsoever to figure out why the circuit behaves in this really, really funky manner.